Okay, good afternoon, morning. My name is Debbie Zipes, and I'm a consultant with the Mott Foundation. I've been helping Carla put this conference together, and I'm really excited for this session in engineering mindset and hearing from Christine Cunningham and a little bit about her background. She's a professor of practice in education and engineering at Penn State. And her work focuses on making engineering, science, and computational thinking education more relevant and equitable, especially for populations that are underserved and underrepresented in STEM. And she does this through, she's done a lot of research, she's developed curricula, she supports pre-K through 8th grade youth and their educators. She's written a book called Engineering in Elementary STEM Education. She was the vice president of the Museum of Science in Boston. She's on the National Assessment Governing Board. She's done a lot of things, won a lot of recognition and awards. And we're really excited to bring her to South Dakota. So I am now going to turn it over to Christine.
Thanks. Welcome everyone to this session. I just realized the date on my slide is incorrect, but I do actually know it's November 18th, and so we're here at the right day. I'm really excited to be here, and I look forward to exploring engineering mindset with you today. It's been such a challenging time recently, and I like to think about it as sort of an opportunity that now more than ever, we need to create a generation of innovative problem solvers, and I hope this session will help you to understand how engineering education can help accomplish that. So as was mentioned, I'm Christine Cunningham, and that was a lovely introduction, so I will move right on from there. In this session today, I want to provide a brief introduction to engineering mindset, and I have three primary goals. We'll start by situating engineering within the STEM disciplines. We'll explore 10 critical practices of engineering mindset and take a look at what they look like with youth. And then we'll reflect a little bit on the importance of developing an engineering mindset in youth. There'll be some time for questions at the end, but if you have a question during the presentation, you can feel free to type it into the chat box, and Deborah is going to help me keep track of those, and we'll do all of the answering of those at the end of this session. So let's get started with a quick question to get us thinking. I'd like you to type your ideas in the chat box to the question, what comes to mind when you think about STEM in after-school settings? Folks, are folks able to find the chat box? If you don't see it initially, look at the little thing that says more. There's 3 dots, and under that you can find chat. So I see some folks thinking about it being hands-on, interactive, and having the opportunity to try some new things without worrying about passing a test, which is, yes, a very attractive part of STEM, particularly in the after-school setting. So before we take a look at engineering in detail, I want to consider for a moment how these disciplines interact with one another. And when I think about STEM and the various disciplines, I think about the relationships and the goal of the endeavor. So what is it that each of these different disciplines is trying to accomplish? If we think about that, science is the body of knowledge about the physical and the natural world. So what scientists are trying to do, and scientific work is trying to do, is describe, explain, and predict the natural world and its physical properties. So for instance, scientists might study when and why we see phases of the moon. They might determine which kinds of genetic changes produce a disease, or they might create models and equations that describe how fast an object falls. So they're about describing and predicting. Engineering is the application of knowledge to creatively design, build, and maintain technologies. So engineers are seeking to optimize solutions for problems, needs, and desires, while they have to also consider resources and various constraints. So one of my favorite and shortest definitions of engineering actually came from a previous president of the National Academy of Engineering, which is design under constraint. And engineers have tried to figure out, for example, how people might communicate over long distances. They've designed systems that maximize the flow of vehicles through intersections in a city. And they've created devices that allow people without full use of their limbs to stand and move around. So that's engineering. Technology can have many different definitions. The one that I tend to use is that it's the body of knowledge, artifacts, processes, and systems that result from engineering. And these are produced by humans to solve problems and meet needs. So the smartphone, the coordinated traffic lights and patterns, and the leg braces and prosthetics are all technologies that have been engineered by people to solve a problem. So that's the product of engineering. And then finally, mathematics is the study of numbers, quantities, shapes, and the relations between them. And mathematics tends to use numbers and symbols to describe relationship between these various concepts. So mathematicians have developed constructs like pi, and they've developed formulas that can describe the circumference and area of a circle. They've created imaginary numbers, and they've articulated relationships between sides and angles of triangles. Now, in real life, people move back and forth between these STEM disciplines as they engage in them. So for example, a biologist studying life in a geothermal vent at the bottom of the ocean may need to work either as an engineer or work with engineers to develop the collection devices that can withstand the intense pressure at the bottom of the ocean in order to get a sample that she can study. So in order to do the scientific study of what's going on in those vents, they first must create a technology with the help of engineers so they can just get the data and samples that they need. So given that little overview, it's now your turn to think about whether something is science or engineering. So for each of these items, there's going to be about 5 of them. In the chat window, please write an S if you think it's something that it's the work that primarily a scientist might do, or you can type an E if you think it's the work of an engineer. So the first one is, who develops a stain resistant material? Would that be something that a scientist, S, or an engineer, E, might do? So I see some S's and 1 E. If I were to classify this one, I would put this one primarily as the work of an engineer, because you're trying to create a new product that solves a problem. So that one I would classify as an engineering work, although you're going to have to work very closely with scientists as you do that to understand the various chemical properties. How about this one? You detail the process by which caterpillars become butterflies. Yep, this one is definitely science. It's the work of scientists. They're trying to think about the natural world and describe what's going on, which will allow them in some ways to predict what comes next if you've watched enough caterpillars become butterflies. Okay, how about predicting where an earthquake is most likely to occur? So you're doing prediction in this case. Yep, this one I would also put as science. Again, it's describing or predicting something about the natural world. Develop a process for cleaning water quickly and safely. Absolutely, this is an engineering thing. There's a problem there. We don't have clean water, or we need cleaner water. And so we're going to try to think about how we develop that and what kind of technologies we might create. And the last one is design a hairdryer that uses 50% less energy. That's right. This one is another engineering problem. We're trying to figure out a technology that will help us be more energy efficient. So now that we've talked a little bit about engineering and the STEM disciplines, I want to turn to focus primarily on engineering itself. This is a relatively recent addition to pre-college, pre-K through 12 educational settings. Probably about the past 20 years it's come into being. I was one of the first people to start to think about how to introduce engineering to young children. Watching children interact with the world around them, I saw lots of evidence that they are natural engineers and problem solvers. I'm sure you've seen young children at play designing and redesigning sandcastles, towers, bridges, and forts. They build them, they knock them down, and then they figure out how to make them better. I believe that we need to foster these natural inclinations in our learning spaces, in schools, after schools, and summer camps. Today, we're going to think a little bit about why and how to do that. When I began this kind of work, I wondered what children thought engineers were and what they did. But at that time, there was absolutely no published research anywhere about this. That's how new this idea of introducing engineering to children was. So my team and I did our own. We asked more than 700 children at K through 12 to draw a picture of an engineer at work and describe what the engineer was doing. What we learned is that many children think engineers are construction workers. They're the people who build buildings, bridges, and roads. And you want to note that the kids think the engineers are actually constructing these structures, not designing them. We also learned that children think that engineers are auto mechanics. They're the people that you take your car to when it's broken. And from a child's perspective, this makes sense. Engineering is a new word to many children. It contains the word engine. The thing in the car that their life that they know best that has an engineering is a car. So engineers must fix cars. Some children think that engineers are the people that you call when your computer is broken to fix it. And then finally, we were not surprised to learn that the youngest children think engineers drive trains. That's a vagary of our English language. In other words, a lot of kids don't have very accurate or complete understandings of the kind of work that engineers do. To change this, I began to think about how we can encourage youth to continue to draw on their natural problem-solving proclivities and help them engage in engineering work. I asked, what kinds of work do engineers do? From conversations and research, I distilled a set of engineering practices. These are the kind of patterned behavior that create new engineering knowledge and products. As people engage and become familiar with these, they develop an engineering mindset. Today, I'm going to provide a brief overview of these 10 practices and start you thinking about what they might look like with youth. So the core practice, according to engineers, of engineering, the work that they do is problem solving. Engineers don't just solve problems willy-nilly, however. They use a systematic and iterative process that can be generated into a series of steps or generalized into a series of steps and phases called the engineering design process. So there are many, many different engineering design processes in pre-K through 12 settings. You can Google it and many different images such as these pop up. They have different numbers of phases, which are labeled with different terms. Educators should select one that is age appropriate for the group that they work with. Generally speaking, engineering design processes usually have phases about defining a problem, brainstorming some ideas about how to solve it, making a plan and creating the technology, and then testing it out and iterating. Specifying and referring to a process is helpful because the named steps or guideposts of the process help communicate to children what the organizing frame or purpose for that day's activity is. And thus it can help scaffold them through the process of problem solving. A second core practice of engineering is exploring materials and uses of materials and their properties. As they design, engineers investigate and consider materials properties. These properties affect how materials can be used and which materials are best for certain tasks or designs. So all materials have properties. Something might be fuzzy, transparent, strong, malleable, shiny, and so forth. These properties dictate how the material behaves. So as engineers, including young engineers, design solutions, they should think about which materials they need to use. This is knowledge that children need to develop over time and through interactions with and manipulation of materials and the world around them. Helping kids to name the properties of the materials can also help them build vocabulary. Youth should be encouraged to consider, however, which properties matter for the design that they're doing. So for example, what does a bridge that they're building need to do? Is it important that the bridge is strong? Is it important that the bridge is red? Those kinds of things will help kids think about and choose materials that help them create successful design solutions. So youth should be encouraged to think about the materials that they have access to and the properties that those materials have as they engage in design challenges and select the materials that are most appropriate for the task that they're working on. Another practice is that engineers design solutions to specific real-world problems. So they need to consider context, background information, the needs of their clients, and the implications of their solutions. Research shows us that children, particularly girls and students from underrepresented groups, are more interested and motivated when they can connect what they're doing in school or after-school programs to the real world. So I believe that engineering challenges should use narrative and role models to help youth see how engineers can help people, animals, society, or the environment. That context setting element can be different for different ages and different settings. So for example, youth might start an engineering challenge with a news article or video that describes a problem. That could be something local, regional, or global. Or they might read a short book if they're younger about a fictitious character that serves as an engineer to help youth orient themselves to a problem at hand. As engineers consider the problems in context, they have to articulate the design specifications that their product must meet. These will help them understand whether or not their design is successful. So they need to think about criteria. Those are the requirements. For example, a bridge needs to think about how much weight it might need to bear, how long it might need to be, and the duration of how long it needs to last. But engineers also have to consider constraints. And these are the limits that restrict the design that they build. So they will only have so much money to spend, time to create the design, and they must also consider things like cultural norms, like where people actually want to cross the river as they figure out a solution. So usually engineers need to balance these criteria and constraints, these trade-offs, as they work to optimize a solution that they're constructing. Another understanding that's extremely important for youth to develop is that their learning is all interconnected. And I think engineering really exemplifies this idea. It requires drawing upon, reinforcing, and applying science and math concepts and practices. Engineers use math and science to improve their designs. So engineering activities should also encourage youth to apply their science and math knowledge to solve a problem. Let's see what this looks like. These youth are manipulating magnets. They've been challenged to design a model maglev or magnetic levitation train. In their planning, youth can draw upon their science knowledge to inform their designs. These youth have experimented with magnets and learned that they can repel or attract each other. Now they're going to be calling on this science knowledge to make their train float. You'll see in this video, as kids try to improve the designs they've had, them referencing the magnets and the science behind it to figure out how to make their design better.
All right, so is that connecting or repelling?
On emoji.
Check if that's repelling or connecting.
That's connecting.
Now we will test the magnetic levitation
Transportation system.
Which looks like it's attracting me.
Are you sure?
But what I think is happening is this side here is like a different pole than this. So it's trying to slide over.
Okay.
It's on this one repelling, but it's connecting on this one.
Because if you do this,
Okay, so
it's like it's not
Trying to get
staying straight.
inside there.
Yeah, it's trying to go like that.
So
it's
I
trying to hop
think
itself.
if we made it a little bit wider or lost some of the magnets that run through the middle, it would work better.
And when we improve.
Okay, ready?
Yes, we made it. We made it. We made it. Oh yeah. Oh yeah. High five to everyone. Oh yeah. Oh yeah. Oh.
So engineers think innovatively, brainstorm and analyze multiple solutions, compare the effectiveness of various designs, and make informed recommendations about open-ended problems. The problems that they tackle often have multiple possible solutions, and the solution sometimes depends upon the context. So youth should use their knowledge and creativities to solve problems that are open-ended. They should be invited to bring their background experiences, cultures, and interests to the problem at hand. The opportunity to design something truly unique makes engineering highly interesting and engaging for kids. This teacher's first graders worked as agricultural engineers as they designed a simple hand pollinator, a device that would pick up and drop off pollen to pollinate a model flower. She identifies in an interview that these multiple solutions and various ways of solving the problem was one of the highlights of teaching engineering for her.
I think the variety of solutions that the kids came up with was the most exciting for me. None of the hand pollinators looked the same, not even similar. They used obviously the same materials. They're very creative, they're very different. It was, I think the most exciting part was to watch them try it and then to see the wheels turning and to talk amongst themselves about how to improve it was priceless. I think the variety,
So evaluating designs and iterating them is also another important piece of engineering, a practice of engineering. After they design and create a technology, engineers need to test that design to see how well it works. They collect and analyze data to revise and improve solutions in an iterative process, helping you think about how well their design performed and how it might be improved in the next design phase is an important role for educators. We see a great example of how an educator can encourage youth to reflect on their designs in this next video. This is the kind of work educators can do to help students develop engineering practices as they engage in engineering design. Notice how the educator asks questions that prompt the youth to evaluate their design for a sail that they have engineered. This sail will catch wind from a fan to push a small boat moving down a track.
Let's see what happens. So what do you think? Is it moving? Yeah. Is our boat moving? No. Our boat's not moving. When you redesign this, what do you need to change about the sail?
Like, I need to make it a little bit stiffer.
Needs to be stiffer. So think about what you could do to make it stiffer with the materials that we have.
That looks goofy.
I don't know, his looks different too. His is different from all the others I've seen too. Is it catching? Look at that. Yeah, it is. Do you think there's anything that you could do that would make it go even farther? Yeah. Well, this one's interesting. Let's see. Go. You put it in there. How is it going to go? Before you even start, I have a question for you. Everybody else who brought theirs back here, put it up here on the top. How come you made yours go forward?
So the air could go in there.
So you made it angle forward so that it would catch the air in that way? Interesting. Is it catching the air the way you thought it would? Let's see what happens.
So the sail video, like the maglev video, points out another practice of engineering, that it's okay to fail. Real engineers know and embrace this idea, that failure helps you learn what works. Engineers learn from this failure to revise and improve their designs. This requires perseverance in working through multiple iterations of a design. As you saw, when the youth's first design for a maglev train or sail failed, they recognized that they needed to improve it. In most engineering design processes, an improve or iterate step is built in. So kids know from the very beginning that you get to try and try again, that engineering involves multiple iterations. When an initial design fails, that failure actually helps students learn more as they improve their subsequent design. So they learn that persistence pays off. As you can see from these quotes, youth also embrace the opportunity to hone their thinking and work on new solutions. One child said it was fun to mess up and try again. Another one, now I know how engineers feel when things they design don't work the first time, but I still want to be one. And then a third one draws this out. What I especially liked was when we got to improve our ideas to make the system better. Engineers consider multiple ideas and multiple solutions, and then they also work in groups with multiple people. Teamwork is a central tenet and practice of engineering. Engineers work together to bring a diversity of knowledge and perspectives to a problem. Communicating and negotiating effectively are important skills for teamwork. When youth engineer, the experience develops their ability to consider other people's perspectives, to argue from data and evidence, to compromise, and to select the best ideas. Let's poke our head into a class where youth are working on a bioengineering challenge. They're designing models of membranes that will be used in a habitat for a frog. The goal is to keep the frog's skin moist without flooding the habitat. In previous activities, youth conducted tests to gather data about how fast water passes through various materials they can use, such as cheesecloth, felt, sponges, aluminum foil, and coffee filters. They used this information to brainstorm some possible solutions individually. That gave everyone a chance to gather their thoughts and ideas. Now they're sharing their designs with their teammates to come up with one group design that they'll test. Watch them consider each other's ideas and argue from the evidence they've gathered.
Your goal is not just to pick your design. Your goal is to create the best design to make sure that the frog stays moist for a certain period of time. 6 minutes, begin.
I do the sponge and the cheesecloth because the cheesecloth won't go on top, the sponge won't go on the bottom. The sponge is like soaky.
But the cheesecloth
And
get a
the
little
cheesecloth-
soakier than faster.
But I don't agree with that because, like, you know how when we put the cheesecloth, when we put the cheesecloth, it's not taller.
Mine's different. I put the sponge on top instead of the cheesecloth because the cheesecloth gets wetter and it pours all the water to the sponge and it drips fast.
You can put y'all two because y'all
Together.
But I put the coffee filter.
Oops.
Yeah, I can put that.
Then we can put all of it together.
Can't put all of it together.
You can use the sponge. You can use the felt. And
You can also use try the cheesecloth.
Those were good ideas.
Now, I will say, I'm enjoying the conversations. You guys are really trying to think about it. A lot of you are trying to compromise and work with one another.
So youth will vigorously discuss their design ideas and argue for their perspectives. I recommend that young children work in pairs, and as they get older, that youth work in groups of 3 or 4, because the larger groups allow for this type of important dialogue as well as a diversity of perspectives. All of this requires youth to negotiate, but such teamwork mirrors how engineers work as well.
Your goal
Does not like my clickers today. Finally, the last practice is engaging and identifying as an engineer. So engaging in engineering design challenges can help youth to understand what engineering is and see their own potential as engineers and problem solvers. We see a wonderful example of children self-identifying as engineers and connecting the work that they do in this class. They've already learned about a girl who wants to design a wall to keep some rabbits out of the school vegetable garden. They've also conducted a controlled set of experiments to evaluate what materials might make the best mortar for a stone wall. Next, they're going to design and build their own walls and test their strength. But before they do, their teacher poses a really important question.
At this point, do you guys feel like materials engineers? Yes. Why? Anybody? Yes.
Because we already did like 3 of the engineering design process. Okay. And we asked the question and we answered what are solutions.
Okay. Anybody else? Do you feel like a materials engineer and why? What makes you feel that way? Yes, Marcus.
Because since I've been here all 3 days of our material engineering process, I feel engaged and interested in what's probably going to happen next, just as a material engineer would, and I think I'm really ready.
You are? Okay, wonderful. I think you guys are all ready too.
So to grow up to be engineers or problem solvers, youth need to be able to imagine themselves in this way. And engaging in engineering challenges can help children do so. Educators can help develop these identities by engaging youth in authentic experiences and labeling the work that they do engineering. As youth engage in these practices, they can develop an engineering mindset. They will develop confidence in their engineering abilities. I know this was a really quick introduction because our time today is short, but there's a lot more information about these practices and engineering on the STEM Next Opportunity Fund website, which I show you here, and we'll also post this URL into the website if I can get the right information. Just a second, let me copy this. You should all have that URL. On this STEM Next page, the practices are explained in more depth. There are some additional webinars that explain them more. And there are also some engineering activities for out of school time settings that can help youth engage in such practices. These include an educator guide and engineering notebook for after school and out of school youth. Generally, they take about 90 minutes and we design them so that you can do them either in person or they can be offered virtually. Now that I've outlined what some of these practices are and provided examples, I want to give you a chance to watch classroom footage of youth engaging in engineering to observe and reflect on these practices in action. So take a brief minute to look and review at these 10 practices for an engineering mindset. I'm going to show you a short video. And what I'd like you to do is think about which of these you observe. And I'll post this list as well in the chat box so you can look at them simultaneously. In this video, we see Julie's class work as agricultural engineers to design the hand pollinators. This is a formal education setting, but children in after school or out of school settings can do very similar kinds of engineering. As you watch this video, I'd like you to think about where you see students engaged in the engineering practices. And then I'd like you to I'm going to post these practices in the chat box in case you want to glance at them. And then after the video is done or while it's going, you can put the number of the practices that you observe in the chat box. So the practices are in the chat box, and let me play this video.
We're going to make a hand pollinator. The hand pollinator needs to go to a flower, and when it touches the pollen, pollen needs to stick to it. And then when you go to another flower, the pollen would what?
Stick to that one.
Drop off and stick there, and take more and bring it to another flower. I want you to brainstorm ideas for your design.
I have an idea. We could use this one and then just bend it. Yeah, okay. So let's say number 3, but we'll just bend number 3. How about that? So it'll be half of my, it will look like your idea, but it will do the things that are in my idea. So it's both of ours mixed up. Yeah, but how are we gonna put the pom-pom on? Pom-pom? Put it on top. Look what we've created so far. Use the foil and use the pipe cleaner. Yeah. So we're cutting the fur off and putting the fur on. Yeah.
All right, let's see if this hand pollinator works. Would you say your hand pollinator worked this time?
No.
What do you need to do?
Improve.
Good job. Here we go, testing. 1, 2, 3. Good job. 3-tap test. Okay, lift up your flower. Whoa, did it work?
Yes.
Well, congratulations. Give them a hand.
Okay, so take a little minute and think about that video and what you observed. Did you see any of the engineering mindset practices within it? If you did, you can type the practice number or numbers that you observed in the chat box. Yep, so people are seeing, they saw the kids persist through the failure when it didn't work the first time. They knew they were going to go back, and you did not see tears, which is a big thing when you're 7, that they understand that they're going to get to go back and try again. That's part of engineering. The kids are paying attention and working with each other in that small group. That's also something that at age 7 is not always something they can do. A lot of times there's still a bit of parallel play going on. They were thinking about some of the materials and their properties. I think someone wrote down. That's another one that they've thought about. Looking at multiple solutions, evaluating designs, and working in teams. So just in that little clip, which obviously was taken from a number of days in a classroom, you can see how as kids engage in these kinds of engineering activities, they come to participate and engage and understand that this is the kind of practice that's important in engineering. We personally, in the work that we do, don't emphasize so much what is the content takeaway, but rather how can we get kids engaging and understanding that these kinds of approaches to problems really help them get solutions that eventually work as they engage in persistence, teamwork, and thinking about the data that they're receiving. Okay, so why is this important? Providing authentic and meaningful engaging experiences for youth help them to develop these practices and an engineering mindset. But why do we think it's important? I'd like to give you folks today a chance to discuss this and to think a little bit more about how these engineering ideas and mindsets and practices can be applied to the work that you do. In a moment, we're going to send you out to a breakout room with about 4 people. And in this breakout room, I'd like you to discuss the following 2 questions. First, why do you think that developing this engineering mindset in youth is important and might help them? And second, how might you introduce these kinds of practices into an existing activity or something that you do already in your programs? So a little bit about the breakout room logistics before we go there. If you haven't already, you can turn your video on when you're in the breakout room so folks know who they're talking with. If you can introduce yourself and share your birthday month, and the person with the month that's earliest in the year will be responsible for sharing out 1 point of discussion when we return to the group in the chat box. You'll have, let's give you 8 minutes to discuss. And my understanding is that there'll be about a 60-second countdown before you're automatically brought back into the main room. So if you're in the middle of a point, you can wrap it up. And then once you've returned to the main room, that person with the earliest birth month, if they can type at least one thing that you talked about in the chat box, don't do it in the breakout room chat box, because that will not get sucked back into our general conversation, and the rest of us won't be able to see those. So I will give you a little time when we return. So if the tech folks would like to send folks into the breakout room, I will see you all again in about 8 minutes, and we'll continue the conversation. I will also post these questions in the chat box, by the way, so you remember what you're talking about. So we're Alex. Alex is our tech guy. Okay, here he goes. Okay, we'll see you soon. Hi all, welcome back again. We're waiting for a few more people to join us. Oh, you know what? I think I need to share my screen again. Possibly. Okay, that I was wondering why it wasn't working. So welcome back all. If we can take a quick moment and have whoever is the reporter drop into the chat box one point of discussion that you had related to either of these two questions. That way we can share what we've learned as a group. So why is developing an engineering mindset important, or what is something you might do to help your students, your youth that engage in your programming, start to get introduced to these practices and the idea of an engineering mindset in general. So if folks can put that into the chat box, that would be great.
Here I was getting all ready to give a speech.
Okay, well, you know what? Since we're such a small group, I think we could also do that because we don't have a huge number of people. So why don't we do that? Was that Laura that just said that?
Yeah, that's
okay,
mostly because I like to talk and I hate to type. So.
Well, we're a small group, so let's go for it. What did you talk about with your folks?
Well, it was Deb and Ariana, and from Indiana and Black Hills State University, and I'm coming out of Vermilion. And we had some technology problems hearing one of our members and seeing her. And so I thought that that was very apropos because we're hoping that the youth are going to solve all of our technology problems. So the next time we have to do a breakout room, we'll be all set.
Great.
Yeah, so there you go. We're really hoping for the youth to save us all, basically.
And Kaylee, do you want to talk a little bit about what we did in our group?
Yeah, so we talked about how important it is for children to develop that mindset at such an early age, and then they can then take it, they develop it at a young age, and then it just progressively gets better as they get older. So that was kind of what we talked about.
Okay, great. Well, I hope this session gave you some initial ideas about how you might help youth to think about engineering practices. I know there are a couple other sessions at the conference, including those in the next hour, that have some more additional connections to STEM. And so hopefully that can continue to build on this kind of trajectory and knowledge. And I can now at this point in time take any questions that you might have, but I thank you for spending some of your valuable time here today. So and since we're such a small group, if folks don't even need to write them in the chat box, you can just ask away if there's anything that you'd like to hear more about. Nothing. Okay, well, in that case, I'll put the toolkit I mentioned with the activities. I'll type that URL again in the chat box in case you want to access any of that. Baking your politics, good idea. That's really interesting. So baking first, I would say there are definitely some ways that you could think about connecting baking or cooking and engineering. And some of them is to think about engineering as a process and also the outcome of what happens when you put things together. So many of I would argue that you can think about a recipe or some of the canning or other kinds of things we do as technologies that are handed down from generation to generation. So if you make items or different types of food in a certain order, like there's a reason that we put that most recipes start with having the butter and the sugar cream together at the beginning and not just throw everything in a mixer and mix it up. So one possibility is to get the kids thinking about why it's done that way, what results by having that process, having them thinking of writing their recipes down or bringing in recipes and looking at them and trying to think about like, well, if we do something differently, what happens? So for instance, I know I did a STEM project in elementary school where I made very small batches of muffins, and in each one I left out one ingredient to see what happens. And from that, you start to understand the role of each ingredient in creating, those muffins. If you leave out the leavening agency, they're flat as bricks. If you leave out the, eggs, they don't rise at all. And getting kids to think about the food that the processed food, I should argue, the stuff that we buy in containers has many, many forms of engineers involved with it. There's lots of chemical engineers that think about how do you make your cheese or your ice cream just a certain creamy texture. Kids can't do that yet, but I can tell you, you read the side of those boxes, all those ingredients with big long names are all chemical engineers hard at work trying to convince folks that they want to buy their products. So I think helping kids to think about what goes into products and how each of those ingredients has a role to play is one connection. And then also how the order in which those ingredients get put together really matters. And thinking about, what needs to be communicated in that technology that gets handed down, that recipe card that gets handed down, is the accumulation of many, many people trying to solve the problem of how do I make a cake or a muffin or a stew in a reliable way that comes out the same every time. Politics is a little more problematic. I think the way that I generally would try to think about politics is connected to the implications of technologies. So as we engineer any kinds of solution, like if you're deciding where are we going to put a wastewater treatment plant in your town, the situating of that building is as much a political endeavor as it is an engineering endeavor. So engineers need to think about where that makes sense in terms of you need to have access to a stream or a place that water is coming in and more importantly being dumped out into. But there's a whole bunch of politics related to how is that funded? Where in town does that go? Whose neighborhood does it get put into? So the politics is not so much an actual construction of the device itself, but rather I would say the formulating of the criteria and the constraints. And in fact, in the curriculum project that I'm now working on with my team, we have the kids explicitly think about the implications of their technology and which kind of people or populations are benefiting from or being harmed by the technologies that are created, because so much throughout time, the benefits accrue with one set of folks and the harm, like if you have a chemical plant and it's spewing population or spewing something else or spewing pollution or spewing noise, like those tend to get situated in certain parts of town. And let's just say they're never the extremely wealthy parts of town. So getting kids to think about the fact that there are larger implications to the technologies that they create and bringing those to the fore as criteria and discussions that should happen in concert with politicians, I think will help us create technologies whose impacts are far more recognized and distributed across the population. So those kinds of things are ways that you could potentially tie politics in. Like if you had your kids like try to, for instance, clean up a little baby oil spill, that gets into politics really quickly about, should we have these oil tankers? What if we do have them? What kinds of regulations are there about how the ships are constructed when the ships do break a leak or sink or something? What happens and how is that played out? Is all then goes, part of it is engineering and the technologies that they're going to use to clean it up, and then a huge part of it is how does that intersect with the political nature, the funding that's available, the way that this is communicated to the public. So I think there's a very tight link between the creation and the implementation of engineering solutions, because without the funding and the larger society sort of ensuring that there are, meaningful regulations, we can get into some bad spaces.
Well, thank you
Okay,
so
well, if there's
much.
no
This
other
was
questions,
really
we'll let you folks go, but please feel free to reach out if you have any, if there's anything else I can do for you. And I encourage you to, check out the STEM Next website for resources there that might help support you or the educators that, the other educators you work with. So good to talk with you all today.